Welcome. In today's video, we're going to look at applications of moment generating functions. But before we begin, let us really understand, why is it called a moment generating function? And here's a little bit of an introduction. The MGF, or the moment generating function, is so named because it can be used to find the moments of a distribution. And that's quite simply why. So let I denote, or let mu I denote the ith moment of x. In other words, let mu I equal x to the power of the ith moment. Now, if we were to express the moment generating function in mu I, we can do it in the following way. And let's take a look. So, and this will show us really why it's defined the way it is. If you take the moment generating function, and recall we've defined the moment generating function before in a previous video, it's the expectation of e to the power of tx. Now, if we're smart, and hopefully we are, we know something very important about the exponential distribution, the exponential function, namely the exponential function in general, e to the y, can be rewritten as a Taylor expansion as 1 plus y squared on 2 plus ... and so on and so forth. Or if we were to write it in another way in shorthand form, we can write it in the form y is equal to 0, sorry, not y, but I is equal to 0. I is equal to 0 to infinity of y to the I over I factorial as our function here, or our exponential. Keeping that in mind, we do have an exponential function here. The only difference is we have a power of tx rather than a power of y. And so we can rewrite the expectation as instead the expectation of a Taylor series approximation to the exponential, or in fact, just the Taylor expansion of an exponential. It is exactly, they are exactly equal. So that would become I equals 0 to infinity of, now instead of y to the power of I, it'll be tx to the power of I over I factorial. And if we want to do a bit of simplification here, we note that that is the expected value of I equals 1 to infinity of t to the I x to the I on I factorial. Now, we know one of the properties of expectation, as an aside, and recall that if you have the expectation of, say, a function of x, let's say, a function of x and another function of x, expectation is linear in nature, which means that you can take the expectation of the two functions independently. And for this reason, you'll notice here that this summation you can think of as a sum of a series of functions in xi. So therefore, by the same token, we can say that the expectation of a sum is equal to the sum, I equals 0, sorry, it should be 0, to expected value of the functions. This is an important property in or of expectation that we're using here to write this down. Now, of course, one other point to note is another property of expectation. If you recall, the expected value of alpha times a function of x is equal to alpha times the expected value of a function of x. This is another important property because you'll notice that this component, the t to the I and the I factorial, are actually independent of our random variable. They're like a constant. And so they can come out the front of our particular expression. So that becomes I equals 0, to infinity of t to the I over I factorial ex of x to the I. And finally, recall up here we defined our mu I term as the ith moment of x. This can therefore become, we can rewrite this summation here as I equals 0 to infinity of ti mu subscript I over I factorial. And there you have it. This is the reason as to why it is called the moment generating function, because it can actually be expressed as a power series with coefficients mu I over I squared and t b, power series in t. Now, why do we use MGFs? I mean, this is all good and well, and it can be rewritten as a moment, but what are their uses? What are their purposes? And more importantly, in this video, what are their applications? So MGFs are useful for a few purposes. And I'll list them out here, and then over this video or over a few videos, we might cover these purposes individually for several reasons. Okay, so one, they can actually be used as an alternative specification of a random variable. Alternative specification of a random variable. Now, what do I mean by that? As opposed to its PDF, as opposed to its PDF, or in fact PMF, depending on whether you're continuous or not. What does this mean? What I mean by this is typically when we try and represent a probability distribution, we describe it in terms of a probability density function or a probability mass function. But actually, MGFs, when evaluated or when derived, can be used to specify the distribution instead. It is therefore what we actually say is the MGF, if it exists, sometimes for some distributions it might not, uniquely determines the distribution. So that's important, right? If you have two probability density functions that are equivalent, they are unique and identical. If you have two MGFs, which are identical and unique, that gives them the same distribution. We'll look at that in a bit more later. But there is a second reason why MGFs are useful. And while we saw that Taylor expansion above and whatnot, they can actually be used to compute the moments. Compute the moments of a random variable. And we'll see that a little bit later. And in particular, what I mean here is the expected value of x to the n. And why is this useful? Because it sometimes avoids, so while avoiding complexity of integration and summation. Throughout your studies of probability, I'm sure there are many a times where you've had to derive the mean of a distribution, and then you've had to derive the second moment and perhaps even the third moment. And in each case, it requires a different summation, potentially a whole different integration technique. With an MGF, and if you're supplied with an MGF where you derive the MGF, you no longer need to use that. And we're going to see an example of that as well later on. And finally, one of the last more powerful results, perhaps one of the most powerful results of the MGF, they can be used to analyze sums of random variables. And in fact, they're going to be able to help us derive distributions of sums of random variables, which will be quite interesting. But for now, while I have your attention, let's have a look at the first property. And let us be a bit more specific. Like I said, it was an alternative specification. So what I'm going to say is the uniqueness of moment generating, or of MGFs. So here is my proposition, or here is my case. Consider two random variables, and we'll say x and y, such that they have the same MGF. In other words, mx of t is equal to my of t for some reason my pen decided to create that huge line, but I hope you get the picture of my of t, and this is for all t in some predefined set c to c. All right, so it's defined at least for some subset of t of the real number line. It follows that fx of z is equal to fy of z for all z an element of the real number line. In other words, if they share the same moment generating function, they share the same cumulative distribution function. Or in other words, if we wanted to think about it as two separate ways, they share the same probability density function, or they share the same probability mass function. That is what the uniqueness of MGFs imply. And so I'll write that in maybe a bit more English. That is, if two RVs, random variables, share an identical MGF, then they also share an identical distribution function. This can be very interesting. Now, I'm going to present you here now with a table of different random variables that we might have covered in our study of probability and statistics. And I'm going to give you their respective moment generating functions. To see this in a bit more detail and how we derive these moment generating functions for these random variables, I encourage you to look at some other videos on the channel because each of those derivations takes quite a bit of time. So what I'm going to do is instead I'm going to present you with a table of some common ones. And here it is. So here we have our table where on one side we have the distribution. So here we've got some very common, both discrete and continuous distributions from the Bernoulli distribution, binomial distribution, geometric negative binomial Poisson, discrete uniform, uniform, exponential, gamma, and normal. And on this side here, we have their respective MGFs. I won't go through all of them in so much detail, but what I will say is just go through an example here. You see if you have a random variable with Bernoulli p as your parameter, then the moment generating function that you derive becomes 1 minus p e to the t, or even say for the binomial distribution, we have this formula here, 1 minus p plus e to the t to the power of n. And, we can go on the list and pause here to copy this down or research them yourself, but these can be taken as given for now. Please see other videos if you'd like to see their derivations. Now, given that we now know this, let's look at an example. We have two examples here. Let's have a look at number one first. So let x be a random variable with MGF 0.6, 0.4 e to the t to the power of 10. Now, let's look at our list of moment generating functions above and see if any of them even resemble this. Okay. First thing I notice is I've got a power of 10. So I'm going to look for things with a power. This has a power. This one has a power. And this one has a power. So that could be interesting. It could be any one of those. Then I notice that there's an e to the t in the expression here. And the only one with an e to the t also in the expression out of the ones I just circled there is the binomial MGF. And in fact, if we look at that binomial MGF and bring it down here, so when x has a binomial distribution with parameters n and p, then mg, or the moment generating function of x, as we wrote up here, was 1 minus p plus e to the power of t to the power of n. Now, looking closely here, apologies, I think I've missed a p in this expression. p e to the t. Notice if I substitute a value of p is equal to 0.4 and a value of n is equal to 10, so I can say when p is equal to 0.4 and n is equal to 10, then the MGF of x, or the moment generating function of x, becomes 1 minus p, which is 1 minus 0.4, which is 0.6, 0.6 plus 0.4 e to the t to the power of 10. And hey, what do you know? That's exactly the moment generating function that I had. So therefore, x has a binomial distribution with, say, parameters 10 and 0.4. So far, so good. Let's have a look at another one, particularly the second case. Let x be a random variable with MGF 1 minus t on 2 to the power of negative 4. Determine the distribution of x. Well, this one's a bit of a tricky one because I've got a power of negative a quarter. And if I have a look again at my functions with even a power, none of them really have a power of, say, a negative power. They've all got positive powers. R, and N, and alpha are all strictly positive numbers. So this could be a bit of a tricky one. But let's rewrite the moment generating function. I'm going to try and write it in terms of a positive power, and maybe that might help us determine which of these MGFs are the one in question. So let's rewrite the MGF. Mx of t is by definition 1 minus t on 2 to the power of negative 4. The first thing I'm going to do here is I'm going to combine the entirety of the expression in the brackets in one fraction. When I do that, that becomes t, or 2 minus t over 2 to the power of negative 4. And to remove the negative, because there's a negative out the front, I can actually flip the inner fraction and then remove the negative, because that's how a negative operates. So it becomes 2 minus t to the power of 4. And now perhaps this is something that is more easier to handle. And now if we have a look, this 2 minus t to the power of 4, does it look like this one? No. Does it look like this one? No, that's a power one. What does it look like? Oh, here's one that might be interesting. We have a gamma function has this particular functional form, lambda on lambda minus t to the power of alpha. So I'm going to write that down. When x simulated a gamma alpha lambda, this implies that the moment generating function of x, we defined it before, was lambda on lambda minus t to the power of alpha, and it specifically was for t less than alpha. That was the defined range for which this function actually exists. Then we noticed that when, say, alpha is equal to, in this case, 4, and lambda is equal to 2, then MGF of x, the moment generating function would become 2 on 2 minus t to the power of 4. And then, of course, for t less than or equal to 2 in this particular instance. and that tells us our distribution. Therefore, x is simulated like a gamma distribution with parameters 4 and 2. I'll stop there in our video and give you time to pause and absorb everything that we've covered. This was the first video covering applications of moment generating functions. In the next video, we're going to look at computing the moments of a random variable using the moment generating function. But for now, I hope this video was useful and how it shows how moment generating functions actually specify the distribution. Of course, thank you for watching. Hope to see you in the next video.